Okay, getting near the end of our bottManager. So what I wanted to do was get a joystick working with my robot. So this is the type of joystick I tried to use first. It's a PS3 wireless controller. ROS2 has some packages out there that already interface to that. So I tried using that, but I ran into problems running that on a Raspberry Pi. So what I changed to using is one of these. So this is just a hardware joystick controller, analog one, and I put it in a 3D case. Put a Raspberry Pi in there, which is running ROS2, and then that sends twist messages to my actual robot base running on another Raspberry Pi. That seemed to work okay, so this video I'll just go through what I did to get that working, tie up some other things to do with GitHub, getting libraries installed, and then I think that's most of the preliminary work done. I may have one more video after this just to tie up any loose ends and tune the robot for movement before getting into the real robot. So I was finding using VScode ran slowly sometimes, so we can have a look at using top to see what the memory profile is, and when I'm running code it goes down to just 262 meg free. So what I'm going to do is upgrade the Raspberry Pi to an actual 8 gig model and see what the difference is. Okay, I'm going to use one of these cases for the updated Raspberry Pi controller. It's an Argon one. It's just a air-cooled case, so connects with the CPU and the whole case becomes a heat sink. I've used one of these before. They seem to work pretty well, and I don't think temperature is going to be a big issue with just running ROS2 and Ubuntu on this Raspberry Pi. Anyway, it doesn't generate a lot of heat like a very graphic application. Okay, so I've put the heat pads on there. And just a minute, putting the top of the case back on. And screw it down. It's looking good. So all set. And that top was just magnetic. Okay, I upgraded my Raspberry Pi with the 8 gig model, so from 2 gig up to 8 gig. I'm running top at the moment, nothing much running on the actual Raspberry Pi. So let me go over here and run code. That's better. So code started up, and we can see here it's dropped down to 6.3 gig of free memory, so that's a ton of free memory, so much better than when I was just running on 2 gig. So testing out code with the upgrade, it seems to be a lot faster. It doesn't have the delays that I saw with the 2 gig Raspberry Pi. So I'll use this model for my actual robot. I think I could have got away with a 4 gig Raspberry Pi, but there really isn't much difference in cost between the 4 and the 8 gig. Okay, just checking where I am with the preparation part of this project. So I go into my checklist. So I've completed the microcontroller to ROS interface and created a Raspberry Pi ROS controller, or the ROS2 node. I'm not going to do the lithium-ion tasks. I think I might leave that until after I've got the robot running before I work on the batteries. And then I won't be doing this build distance mapping sensor as well. They'll sort of come later when I've got the running robot and get deeper into navigation. But I think I'll do this. I want to be able to send twist commands from a joystick rather than having to type them in through the keyboard. It'll just be more responsive and more useful once I get the robot running. So I'm going to create a joystick controller. That's what I'll look at for the rest of this video. And then finally I just need to wrap up, put the things together, plan for my robot. So I'll just go through a bit of the design work for the joystick that I want to use to run the base motor controller. I've actually gone through some of this, so I'll just take you through some of the design missteps along the way. So first I thought I could get just one of these handheld PS3 controller, which has a little USB wireless connector that you can plug into your Raspberry Pi, and then I'll take the input from that, and there's a couple of ROS2 Foxy packages out there already, one called Joy Node, one called Telop Node. So one will read that serial input from the joystick controller, produce joy messages, and then this Telop node will take those joy messages and convert them to twist messages. So I tried that, but I found this node here wasn't working properly on a Raspberry Pi. So the next thing I tried was used an i386 based Ubuntu host and ran the same thing. So connected the serial connector into that, and in that case it could recognize this handheld controller, generate joy commands, and then create the Telop node, or have the Telop node create twist instructions. So that was working, and I'll show you some of that as we go through it. But I didn't really want to have another machine, or at least a 386 machine running. I was running this on a spare laptop. So the third option, and this is the one I'm going to go through mostly in the video, is to create a standalone joystick controller. So I'm going to take one of these analog joysticks. This is just one I got off on Amazon. Read the voltages with the ADC to I2C converter. Read that into a node on a Raspberry Pi. So I'm going to use that old 2 gig Raspberry Pi that I've got hanging around now. To read that, I'm going to create a node to actually read the I2C and send out twist messages. So this whole thing here will become kind of a standalone 3D controller, so it'll be useful for playing around with, and I use Wi-Fi connection from the Raspberry Pi to have the twist messages sent out and being received by the robot. So let's have a look at the details of that. To show you the trouble I had trying to connect the PS3 wireless controller to Raspberry Pi. So at the moment it's not plugged in to the Raspberry Pi, so I can just do a LS USB. It shows 4 devices at the moment, so let's plug in the PS3. Now let's have a look at the LS USB. So it found one more device. It's just identifying as a USB 2 hub, I think. Yeah. So let's try a look at the logs for USB info. So we see here it kind of saw the product, but it didn't end up being identified as what it saw here on the LS USB. So let's test it out using a ROS2 run joy node. So if there's a joystick there, this should pick it up, and at the moment I'm just seeing crickets. So normally it would display a message saying it's connected to the joystick. Okay, let's try the same thing but on a i386 laptop. So this is the Aspire test. So first let's do a LS USB. I've plugged in the PS3 receiver, and now we see another device here, and it's correctly identified this time as a PS3 receiver. Let's have a quick look at the system log. Again, it identified the device, and we saw it in the LS USB. So let's run ROS2. And this time it identified the device and seems to be working with it with the Joy node. And one more check, I'll just subscribe to the Joy messages so we can have a look at that. and we see lots of messages being sent from the joystick. Okay, even though I could make it work by adding a laptop into the architecture, I don't really want to do that. So I'm going to create a standalone joystick controller. So basically that third design option I showed earlier, using a hardware-based joystick. Okay, to get started on the joystick, I made a quick 3D print for a case, so we can see it here. Basically got mounts for the Raspberry Pi will go over this side, the ADC will go down here, and then the joystick will be mounted there, and then from the front it will look something like this. At the moment I haven't worked out a place to put the battery, so I've just made a USB-C access point to the Raspberry Pi board. So I think I'll be redoing this later on once I get a feel for what it feels like and where things should really be located, but at least this gives me a place to mount my components and start working out the software I need to get it all going. Okay, here's the joystick controller. I made a 3D printed case, so really just got a space for the joystick controller in the top, and then inside I've got the Raspberry Pi connected to the joystick controller, which is analog, and then I've got a AD1115 analog to digital converter that goes through the I2C interface to the Raspberry Pi, and I've got a connector on the outside to connect the USB power at the moment. One more quick sidetrack while trying to get the new Raspberry Pi working. I had to install the copy of my Git repository for ourBotManager _ROS onto my new Raspberry Pi. So the way I found out I had to do that was I created an empty ROS2 _WS folder. Then I did a git clone of my repository to dot, so it puts it all under ROS2 workspace. Then I had to do a colcon build. So the important thing here was just to start with an empty ROS2 workspace before doing the clone. After the colcon build, everything was good to go, and it built all the structure that I needed underneath, and everything was working. Some other things I had to do to set up the environment on the joystick controller. So I had to add the supporting Python libraries to access the I2C interface and the ADS1115. We see the commands there. I could do a I2C detect to make sure that the I2C device was visible and in the right address. And then finally, if you get permission errors when you're checking for the I2C device, I just included the command I used to fix the permission errors, which is kind of overkill, but works. Okay, let's have a first look at my joystick node code. So one thing I used was this library Adafruit ADS1X15, which makes it easier to read the analog to digital converter. Then I create a class, it's called JoyNode. During the initialization, it tests to see whether it can connect to the I2C interface. It'll drop out of the node if it can't. If it can connect, then it sets up a publisher to publish to the base twist message. Sets up a timer. Every 1/10 of a second it's going to go out and check the values on the joystick, and then just sends a notice that the node has started. Okay, so this callback for this timer, which it calls every 1/10 of a second, is called process joy. So it's going to retrieve values from 2 analog to digital converters, one for the vertical, one for the horizontal joystick directions. Sets those values initially to 0, and then goes through and tries to read the values from the ADC for those two values, the vertical and the horizontal. Does some error checking. I found I had to put the sleep in here. It must take some time to settle after each reading, so I sleep for 100th of a second. Seems to work. And then I do just at the moment just log out the values I've read, and I wanted to keep them between a 0 and 100, so dividing by 265 for me gave me that range of values that it reports out on. So let's have a quick look at this working, and then we'll come back to the code after I get the whole thing done where it's actually publishing twists. Okay, let's have a look at the code running. So I'm going to start my ROS2 node on that joystick controller, and you see it's reading the values. If I move the joystick around, you see the values change. Okay, now just go through the updated Joy node code. So now I've got it publishing the twist messages, and there's all sorts of conversions and additional things added to support it running. So there's a whole bunch of more constants and things defined here, which makes sure it works correctly with the actual hardware I'm using. So this I might change it into parameters if I do more work on this, so that when you fire this up you can just set these parameters for the particular joystick that you're using. But let's look at the main changes. So this process Joy, before I had it just going down here showing the values that it was currently receiving from the joystick hardware, but now we're going to process those values and send twist messages depending on the status of the joystick. So first here we convert it into a value from 0 to 200. Actually it'll be from -100 to +100. Range for X and Y directions on the joystick. Sets the polarity, so depending on how I wire up the potentiometers on the joystick, the polarity may not be the polarity I want, so it uses that global constant to set the polarity for the joystick. And then the other thing I do is I don't always want, in this case I don't want every value that is available between 0 and 100, so I use this granularity setting because I only, for my use, having a granularity of just a value of 5, so seeing the values move between 5%, 10%, 15% movement on the joystick is more than enough. And that's important because I'm only sending twist messages when it sees a change, so if I have it too granular then there's going to be a lot more changes detected and a lot more twist messages going out. The other thing I do here is see whether the joystick's in 0 position, and then I've got a range of values that could represent the 0 position. So I've set it up so plus or minus 10 is all set as 0 position for the joystick, just to allow some tolerance there and make sure the joystick can just spring back to the 0 position. Then we create a twist message. We indicate whether we're going to publish on this cycle or not, and publishing will depend on whether the position of the joystick has moved since the last time we published, or another thing that can drive up our publish is whether I want to republish. So I've set it up at the moment so every 1 second or 10 cycles through here it just does a republish of the last value, even if it's the same as the current one. And that's really just to make sure I don't miss messages. So the other logic in here is the base doesn't respond to forward linear movements and angular movements at the same time. It'd be kind of a curvy shape if it did that. But at the moment I'm just restricting the base to only respond to either a linear command or a angular command, but not both. So it determines which one to send based on the joystick, whatever's greater, the X position or the Y position of the joystick, whatever indicates what I'm trying to do, will decide whether it's going to do a linear or an angular movement. And then the final condition here is if neither is greater than the other, then the joystick must be in the 0 position, so we just send a twist message indicating 0 position, or 0 linear velocity, 0 angular velocity. And on the base, that's interpreted as a stop message, so it'll make sure the base stops. Here we do the publishing. Again, it's either because I've set a publish, I need to publish because something has changed, or the republish counter has reached 0. So I publish the message and I reset the last values to the current values. So let's have a look at a demo of that. Okay, here's the grand test of the joystick control. So quite a few things going on here. So this first terminal session, I'm connected to the joystick controller Raspberry Pi board that's running ROS2. So on there I'm going to be running the joystick node, or the joy node, and also be watching the bass twist topic coming out of it. So let's start that up first. And every 1 second it's going to push out a twist message just to make sure it's sending the messages. And if I move these, we can see the change in values working well. Now over on the next terminal session, I'm connected to the Raspberry Pi that's going to be located on the robot and is going to manage the bass, so the bass motor controller node. So let's start that up. And this is going to just report on what it's receiving through twist messages. So at the moment, it's every 1 second it gets a twist message with linear velocity and angular velocity of zeros in it, just because the joystick's in the 0 position. And last thing to do is over on the MicroPython code, I'll just connect into the board and we see the stop messages being passed on to the MicroPython motor controller. So we should have all the bits in place. So let's first see whether the motors move correctly. So I'll go to my joystick. So I'll move the Y direction up, which should do a linear direction forward, linear direction back, and then side to side it'll do turns, so turns forward or minus radians. And then we return to 0, which should send the stop message. So generally working. I see one problem is whenever it gets a copy of the last twist message, where it resends it every second, it's causing the motors to sort of shudder. So I'm going to have to look at that. They'll probably be in the next video when I start tuning things up. So it looks like I'm resetting something I shouldn't be resetting between commands. But otherwise, it seems to be going in the right directions, turning the right way, responding to the joystick correctly. So we're in good shape.